Welcome back to Physics 104B. This is Chapter 27, Section 4 on inductance. Look at the picture at the top of the screen. You've got a coil and a current going through it. And then off to the side, there is another current, or there's another coil, which may or may not have a current going through it. And the one on the left, since a current is going through it, you can see that it has a magnetic field. And those magnetic field lines go through the coil to the right. And you've learned previously that a changing magnetic flux going through the coil on the right is going to induce a current. So a changing current in either coil will induce an electromotive force in the other coil. So they have what we call mutual inductance. Well, now I'm going to talk about a concept called self-inductance. Look at the picture in the middle of the page. Here is a simple coil with a current going through it. And this concept of self-inductance, this should blow your mind right here. So it has a magnetic field that is coming from it, as you can see drawn. And remember, that magnetic field is produced by the current. The magnetic flux from this current passes through the circuit itself. So when we change that current, that changes the magnetic flux through the coil, and that will induce an electromagnetic force that will oppose the original change in current. That is very weird. Well, let's take a look at that. So again, here we say that we see the change in current produces a magnetic flux change, and that will produce an EMF. And remember, the induced EMF always opposes the change in magnetic flux, which means that EMF that's induced is going to oppose our change in current. The induced EMF opposes the change that produces it. It's opposite the original current, and we call it back EMF. Called back EMF because it always goes in the opposite direction of the current. The result is, if you have a loop with a current going through it and you try to increase the current, there will be a back EMF produced that will make it harder to increase the current. If you try to decrease the current, the back EMF will make it harder to decrease that current. In electronics, we have something called an inductor, and there you see the symbol for it. Looks like a coil, and we've used it in our circuits, an inductor. It consists of a wire coil. When a current is steady, the inductor acts just like a wire. However, when the current changes, an induced EMF will oppose that change in current. And so we say that it has what's called self-inductance. We use, for the self-inductance, the letter L, capital letter L. It's defined as the ratio of the magnetic flux through the inductor to the current in the inductor. The units are Tesla's meter squared per ampere, and that's actually defined as 1 Henry, named after Joseph Henry, and the plural of it is henries. It's determined by the inductor's physical design. Let's look at an example in the book, example 27.6, calculating the inductance of a solenoid. A long solenoid of cross-sectional area A and length L has N turns per unit length. Find its self-inductance. So here we have the picture, length L, cross-sectional area A. What we're going to do is assume that there is a current going through it, I, and then calculate the flux, magnetic flux, if there were such a current going through it. Well, we know from previous lessons that the magnetic field in a solenoid, produced from a solenoid, is mu naught times N times I. And the magnetic flux for one loop is the magnetic field times the cross-sectional area. Now, if we have many loops, it's going to be the number of loops or the number of turns times B times A. The number of turns is going to be N, which is the turns per length, times L. So the flux then becomes N times L times B times A. Putting it all together, the flux is N times L times B, which is mu naught N times I, times A. So mu naught N squared AL times the current I. And then when we find the self-inductance, that's going to be the flux over the current. So it's mu naught N squared times area times length. Let's look at how we can calculate the induced EMF of the inductor. We'll start with the equation I gave before, the definition of self-inductance, that L is phi over I. Let's take the time derivative of both sides of the equation. So we have d dt of Li and d dt of phi. And that becomes the inductance times di dt. Inductance is constant, so we'll put that to the outside of the derivative, equals. And remember, by Faraday's law, the time derivative of flux is negative of the EMF. So rearranging that equation, we get that the induced EMF is negative L times the rate of change of the current. EMF is induced in an inductor L when the inductor's current is changing. So here we have a picture, there's an inductor, and let's say the current is going from left to right. Now, if we decrease that current, then there'll be an EMF produced that is to the right, as if it's pushing. There's a decrease in the current to the right, so our induced EMF is going to fight against that. It's going to push more to the right, so the EMF to the right is positive. If we try to increase the current, then the EMF is going to push back to the left against that. So we can say that the EMF is negative, or to the left. Here's a got it question. In the book on page 478, it says current flows from left to right through the inductor shown. A voltmeter connected across the inductor gives a constant reading and shows that the left end of the inductor is positive. Is the current in the inductor increasing, decreasing, or steady, and why? So you can see I've got a voltmeter hooked up there, and it shows that the left side is positive, the right side is negative. And we say that the current it must be increasing because there's a back EMF that's pushing towards the left. It's positive to the left, so it's pushing to the left, and that would be as a result of the current increasing to the right. Example 27.7, a dangerous inductor. It says a 5 ampere current is flowing in a 2 Henry inductor. The current is then reduced steadily to 0 over 1 millisecond. Find the magnitude and direction of the inductor EMF during this time. So here we have the given information. There's a picture with the inductor and an external circuit down below. Now, the EMF of the inductor is negative L times di dt. And what's going to produce this is, what's important here is the rate of change of the current. It's a very quickly changing current. So we have negative times 2 Henrys times, it is negative 5 amperes, because it says it's going from 5 amperes decreased to 0. So negative 5 amperes over 10 to the negative 3 seconds. And what we get is plus 10 to the 4th volts. So this induced EMF is 10,000 volts, and that is potentially lethal, even with a low voltage battery. The answer is unrelated to the battery or whatever is supplying the inductor current. One could have a 6-volt battery and still be electrocuted opening a circuit with a large inductance. Let's look now at inductors in circuits. Remember from chapter 25 that the voltage across a capacitor cannot change instantly. It takes a bit of time to build up that voltage and that charge. The current through an inductor also takes time to change. Look at the circuit here. You can, as you examine it, you see a battery, some EMF, and we've got a switch. And right now it's an open circuit, no current is flowing, but what we're going to do is turn that switch to A. And you see when we close the switch on A that we're going to see a current start to flow. In the resistor, it begins to rise. And by the way, if the inductor were not here, I'm going to cover it up right there. If the inductor were not there, then the resistor's current would rapidly go up to the electromotive force of the battery divided by the resistance. So we would just have a battery and a resistor, and by Ohm's law, it would just be the voltage over the resistance. But there is the inductor there. There's a self-induced EMF, and we'll call that E sub L, which opposes the rise in current. So it opposes the battery's EMF. And therefore, the resistor feels a difference between the EMFs. You have just the E from the battery pushing one way to the right as it goes to the resistor, but then you've got pushing to the left the E from the EMF from the inductor, and that's negative L di dt. As time passes, the rate of the current increase goes down, and so the back EMF will decrease as well. The current will asymptotically approach what Ohm's law tells us should be there if there weren't an inductor, E over R. You can see in my diagram right there, we've got the current going from left to right through the resistor, but there's this competition between the voltage from the battery and the back EMF from the inductor. Let's see what the loop law tells us about this. Here I've drawn an X with a circle around it. Let's start at that X and work our way around clockwise and apply the loop law. So we've got negative IR. We then have plus the back EMF, E sub L. And I wrote a note down there, don't worry about the direction for now. Let's just say it's plus. And plus E naught from the battery. And coming around, finishing up the loop law, they all equal to 0. And then let's rearrange it a bit. Let's get the two E's on opposite sides of the equation. So IR minus EL equals E naught. And then I'm going to take the time derivative of that entire equation. So we have R times di dt plus the time derivative of negative E sub L equals the time derivative of the voltage from the battery. Well, that's constant, so the time derivative is 0. Here we have it again. We'll rearrange these terms a bit for this line, and we get the time derivative of E sub L is equal to R times di dt. Now I'm going to do a little substitution here. The left-hand side, I'm not going to mess with that, but on the right-hand side, di dt. And I want you to remember, look over here in the light blue to the right, that E sub L is negative L di dt, so that we can say di dt, we're about to substitute for this, is equal to negative E sub L over L. So let's take that value for di dt, plug it in to this equation back on the left, and we get this, that the time derivative of the back EMF, or E sub L, is negative R E sub L over L. So we've got this equation that relates, there's this proportionality between the time derivative of the variable and the variable itself. The solution of this equation is that the EMF of the inductor, E sub L, is equal to negative E naught, so that's from the battery, times E, and now this E, sorry for all the different E's, this is the base of the natural logarithm, about 2.718, to the negative RT over L. And this looks a whole lot like for an RC circuit. We learned this back in chapter 25, that current for an RC circuit is the voltage over resistance times e to the negative t over RC. Now, the current is equal to the sums of the voltages. So we can say the voltage of the battery plus the voltage of the EMF, and keep in mind they're going to be competing against each other, but for now I'll just write it as a plus sign, divided by the resistance. And here we see that competition, it comes from the negative sign, that subtraction that's actually going to take place. So the current is voltage naught plus negative voltage naught e to the negative RT over L divided by R. Let's simplify that a little bit. Let's factor out the voltage naught or E naught over R, and we get this upside down exponential decay. And you can see the picture in the middle of the page. So if you look at the equation at the top of the page, and it's reminding us, it should remind you of the equations that we saw with a charging or discharging RC circuit. And you see what that base of the natural log, that e, to the exponent it's put to, negative RT over L. Now for a capacitor, we had a time constant. There I've written it as tau sub c as RC. The analogy for that with a resistor inductor circuit is the inductive time constant. So in that case, it's L over R. So for a capacitor, the time constant is R times C. For an inductor, the time constant is L over R. Significant changes in current cannot happen on timescales much, much less than L sub R. And there you can see that upside down exponential decay that asymptotically approaches voltage over resistance. And after several time constants have gone by, the current just becomes the voltage from the battery divided by resistance. It's now the current has steadied off, and so if current is no longer changing, then you're not going to get a back EMF, so that goes to zero as time increases. Let's look at example 27.8, firing up an electromagnet. It says a large electromagnet used for lifting scrap iron has a self-inductance of 56 henries. It's connected to a constant 440 volt power source. The total resistance of the circuit is 2.8 ohms. Find the time it takes for the current to reach 75% of its final value. So here I have the given information. Notice how I've written this, that the current, we want to know when it's going to be 75% of its final value, which is the voltage from the battery divided by the resistance. So we use the time-dependent equation. Current is voltage naught over R times 1 minus e to the negative RT over L. And we're going to substitute for current 0.75 voltage naught over R. You see voltage naught over R, that divides out of the equation. And then we're left with, if 0.75 equals 1 minus e to the negative RT over L, then e to the negative RT over L is 25%. We're going to turn this exponential equation into a logarithmic equation in order to solve for t. So the natural log, because it's log base e, of 0.25 equals the exponent, negative RT over L. And then we go ahead and solve for t. So t is negative L over R times natural log of 0.25. Plug in those values and we get 28 seconds. And by the way, we can compare that with the time constant, L over R, which is about 20 seconds. This picture at the top of the page shows a circuit with a two-way switch, which I introduced earlier in this lesson. We throw the switch to A and the current builds up as I've described. But then if we turn the switch to B, And current continues to flow through the inductor and the resistor because the inductor current can't change instantaneously. So you have it going through like in this picture. I give this to you without going through the derivation, but the current is going to be just similar to a discharging capacitor. The current is going to be I naught, the original current, times e to the negative RT over L. To summarize, what we've seen in the past few lessons is that capacitors store energy in electric fields. We saw that several chapters ago when we first learned about electric energy and capacitors. So capacitors store energy in electric fields. Inductors store energy in magnetic fields. Let's look at this example. You see the picture there with an inductor of 200 millihenries, a resistor of 10 ohms, 12-volt battery. Right now, as the picture's drawn, the switch is opened. The question is, what is the current after the switch has been closed for a long time? And we can think, what do we mean by a long time? Well, just as we talked about when we learned about RC circuits with resistors and capacitors, we can think of a long time as being more than 5 time constants. The current is voltage naught over R times 1 minus e to the negative RT over L. Now, for a long time, and again, we can just take that to be more than 5 time constants, then this e to the negative long time is essentially 0. So the whole thing in the parentheses becomes 1. And then we can say the current is the voltage of the battery divided by the resistance. So after a long time, the current is simply what it would be if you imagine the inductor weren't even there. But it builds up to that. And so we get the voltage divided by the resistance, in this case 12 volts over 10 ohms, we get 1.2 amperes. And my second question is, what is the time constant? So we have tau sub L, and that's the inductance over resistance, 0.2 henries divided by 10 ohms, 0.020 seconds. So in this particular circuit, things happen in the realm of hundredths of a second. And the third question, how much current is there after 10 milliseconds, which is 0.010 seconds. So you compare that with the time constant, and we see it's half of the time constant. When the switch is closed, the current starts at 0, and it's going to eventually make its way up to 1.2 amperes. So we know the answer is going to be somewhere between 0 and 1.2 amperes. Well, let's actually solve it for the given time. Current is the current naught times 1 minus e to the negative RT over L. And current naught is 1.2 amperes times 1 minus e to the negative t over tau. We plug those values in, and we get 0.472 amperes. A fourth question is, what is the voltage difference across the resistor and the inductor at time equals 0.10 seconds? Well, for the resistor, remember that by Ohm's law, the voltage across a resistor is current times resistance. And this change in current at this moment in time, 0.01 seconds, it's 0.472 amperes. So we multiply that by 10 ohms and we get 4.72 volts. The voltage drop across the inductor, because the only two elements other than the battery in the circuit are the resistor and the inductor, and the battery is 12 volts, so you know by the loop law, by the time the current goes all the way around, we should have dropped 12 volts. Well, we already found that the resistor drops 4.72 volts. So the voltage drop across the inductor has to be the remaining that brings it to the full 12 volts. So we'll just say 12 minus 4.72 volts, and that gives us 7.28 volts across the inductor. And that is the end of section 27.4. Have a great day.